All right, Mr. Buckle back with problems number 20 and 21 from your Algebra Chapter 7 self-test. So in 20 and 21, we're going to write an equation describing the situation, and we're going to graph the equations as well. So number 20 says the population, which we're going to call P, of a country increases by 2.5% per year, and in 1980 it had 76 million residents. And we're going to let K be the number of years since 1980. So what we're going to use here is our interest, our compound interest, our exponential function here that says A, which is the total amount, is going to be equal to the principal times 1 plus the rate to the t power. And I know I need to use this function because the change in the situation is a percentage. It's increasing by 2.5%, so since that change is a percent, I know that I have to use our exponential or our compound interest formula. Those two are the same thing, so I'm going to use this because there's a red flag when this increase is a percentage and not the same amount. It's not increasing by 250 residents a year. It's increasing by a percentage, so it's going to be different from one year to the next. So we have this scenario, and we have our equation, and now we're going to plug in the values we know from the situation, from the problem that we were given. So when we do that, we get this function. We get A, which is the total amount, or the population after so many years, is going to be equal to 76. Now the 76 comes from the 76 million, so I'm not going to put this in million. Our answer is going to be in millions. I don't want to write out 76 with 6 zeros, so I'm just going to keep in mind that our answer will be in millions. So whatever our answer is, I just say that many million will be how many people there are. And then we have 1 plus 0.025, and this is because of the 2.5% increase. 2.5% as a decimal is 0.025. So this changes to 0.025 when we plug it into the function because it's increasing by 2.5%. And after k years, I change the t to a k because it wants k to be the number of years. And this is the number of years since 1980. So here's our function right here. This is our function, and this should really technically say p equals 76 times 1.025. 0.25 to the k power because they told us the population p. So this should be a p. That's kind of nitpicky there. Even if I left this as a t, that's fine. We have the necessary information in the function. Now if we graph this function here, this is what we'll get. And again, I stole this straight from your book. Didn't really want to graph this myself, so I didn't. Just stole what you will see. So it's 0 years, at 0 years since 1980. So this 0 years isn't really 0 years. It's 1980. In 1980, there are 76 million people, and that's obvious, I guess, because it says in 1980 it had 76 million residents, so 0, and then this is 76. And then if we plug in 5 in for k and then evaluate the function, we're going to get something out around 82, 83 million, maybe 84 million. I'm not exactly sure what that is, but to get this point right here, we would plug 5 into our function and see what we get out. And again, I don't know what 1.025 to the 5th power is, so use a calculator to figure that out. Multiply it by 76, and it's going to be somewhere around 82, 83 million, somewhere in there, which is where this point comes from. To find another point, we would plug in 10, or we could plug in 15. If we plug in 10 into our function, we'll get something out around 97 million, maybe 98. If we plug in 15 into our function, we're going to get something out around 110 million. And then if we plug in 20 in, we'll get something around 121, 122 million, somewhere in there. So we plot these points and then we draw them. And even though it doesn't look like it, this line is curved because this is an exponential function. And it doesn't have much of a curve because the percent of change here is very small. It's only 2.5% every year. So every year they're only gaining 2.5% more people than they had the year before. So it's not increasing very much, which is why this doesn't appear to be a curved line, but it is indeed a curved line because of that percent of change there. Number 21, the circulation C of a newspaper has decreased by 1% each month since January of 2000, when it was 880,000. And we're going to let X be the number of months since January of 2000. So once again, we're going back to our interest formula. And I know this because our change here is a percentage. It's decreasing by 1%. So we're going to plug in the indicated values here. So C, which is the circulation, how many newspapers are getting delivered every month or every year, it turns out it's a month here, is equal to 880,000. And this is the principal because in January of 2000, that's where we were at. We were at 880,000. We're going to multiply this by 1 minus 0.01, and this is a minus 0.01. Excuse the phone there. And then we're going to evaluate this for the value of X. So, plugging this in, we get, well, actually we're not plugging it in, we're graphing the equation, and we're graphing the equation by plugging in various values. When X is 0, our circulation is 880,000. This is where this point comes from, 880,000. When we plug in 10 months after January of 2000, we get something out around 800,000. And again, plug that into a calculator to find out exactly what that value is, because I don't know what 1 minus 0.01 to the 10th power is. So do that in the calculator, multiply it by 880,000. According to our graph here, it's going to be somewhere around 800,000. So that means 10 months after January of 2000, the circulation was only around 800,000. 20 months after January of 2000, so plugging 20 in to the function for X, we get something around 710,000 maybe. Not exactly sure. You can find that out by plugging this in, or plugging 10 or 20 in for X and evaluating that function. Do the same for 30. Do the same for 40, and you'll find that this is the graph that you will end up seeing by plugging in these various values of X into the function and getting out the corresponding values for C, for what the circulation is. So when we graph this function here, plug in values and find out where we're at 10, 20, 30, 40, 50, 60 months after January of 2000, this is the graph that we will see. And again, this doesn't really look like a curved line. I guess it kind of does. But it's a very slightly curved line because that percent of change is so small. It's only decreasing by 1%. So it is a curved line because this is an exponential function, and this is the line that will come from this function here.